Okay, so hi everyone. So today it's a great pleasure to have Jahanvi, who is gonna who's gonna help us understanding mass loss in red supergiants for our fifth and last talk already of the series. So a little bit about Jahanvi. So she is currently doing her second year PhD in Trieste in Italy, University of Udine, INFN Trieste. She did her master in Isar Mohali in India. And the topic of her PhD thesis is quite completely different from the topic of today, which is optimization and characterization of the divergent pointing mode for the Cherenkov Telescope Array Observatory for transient studies. And she will graduate in end of 2027. So stay tuned if you're interested, and of course you are, about her topic of research. Okay, so I think we can move on to the lecture now. So, Jahanvi, are you ready?
Yes.
Then the floor is yours.
Thank you, Sophie. Thank you to the organizers for giving me this wonderful opportunity. I hope you can hear me at any point. If you feel that the voice is breaking or something, please let me know because I'm not using Wi-Fi, I'm using mobile data. And also, I would like to thank Key for always being there and help me so much in so many questions I asked him during the preparation of this lecture. So in this lecture, we will try to understand the mass loss in red supergiants. But before that, I think it's good for us to start with a little bit of introduction of what red supergiant stars are. So red supergiants are the most luminous cool stars situated at the top right of the HR diagram as indicated here by Betelgeuse and Antares. Very interesting red supergiant stars. I also put a GIF for you. It's beautiful. So how they look in like the effective temperature and the spectral type, I thought that it's better to take the actual observation here to show you that the effective temperature of these stars go from somewhere between 3000 to 4000 Kelvin. And the spectral type goes somewhere between M0 to M5 for these stars. This blue points here are red supergiants, and this red points here are red giants, basically. So now we know a little bit. Let's talk about the formation of red supergiants.
Jahanvi.
Yes. Hello? Hello?
It's okay, ma'am. It was my mistake.
You can go ahead. I muted him. Please, everyone, mute yourself.
Okay. Okay, so I was talking about the formation of red supergiants. So when we have the main sequence, when a star exits the main sequence, what happens is that it exhausts the hydrogen at its core, and then it starts the helium fusion at the core. And then it becomes bigger and bigger, it cools down, and it enters the red supergiant phase. The way that red supergiants can end their life is if it's low mass red supergiants, they're expected to end their life as a core collapse supernova. And if they are more massive, then they can basically turn around and evolve bluebird into the HR diagram. Now that we are here, I would also like to say that between F to G spectral type, we have something called yellow supergiants. And the interesting part here is that these yellow supergiants can proceed and even follow the red supergiant phase. So this is why I said that some of the red supergiants can go bluebird into the HR diagram. So now let's talk about the mass loss. Why mass loss is important? Because we know that most of the mass that a star loses is when it leaves its main sequence star. And not all stars will go directly into the red supergiant phase. A star should be around 8 solar mass. Initial mass of the star should be around 8 solar mass for it to go to the red supergiant phase. And when it goes into the red supergiant phase, it lost a huge amount of mass during that period. And it's easy for it because one of the reason is because the red supergiants has very low surface gravity, which makes it easier for the material to escape the star. Now, this mass loss critically influences the evolution of the star based on how much mass it is losing during that period. And because it's losing a lot of mass and it's losing a lot of mass, it is also contributing to the circumstellar medium uh, by dust formation and all. And then when it ends as a supernova, some core collapse supernova has red supergiant progenitors. And it also decides, the mass loss also decide what will be the final remnant that will stay after this supernova event. So despite being so important, it's very hard to model the mass loss rate for red supergiants. So let me give you this, show you these plots. So first, there was a typo here. It's a 2011 paper, so I corrected it. So these points that you see here, the circles are M-type stars. These are all observation points. The squares and the stars are red supergiants. And what we see here is that we have dotted dashed line, which is Reamer's law, the solid black line, which is the Geneva's stellar mass loss prescription, then Geneva mass loss prescription into 10, and then into 25. And we have, in the end, we have these points, which is VY Canis Majoris, which is also a very well-known red supergiant. So what we see here is that none of this prescription is able to agreeing on all the data points that we have here, which is kind of, I am showing here as well, that if I talk about all these solid lines, which are different mass loss, empirical mass loss prescriptions, except the one which is the dotted one, which is the theoretical model by Key, you can see that except these two, none of them are really agreeing with each other. And so what it shows here is that there is a discrepancy between how theoretically we calculate the mass loss rates and what observationally we see. Also, this is because of the fact that we have some uncertainties in the empirical mass loss rates. So I'm kind of like taking these points by Moran and Jocelyn and showing you here. These are these 8 RSGs which are observed in circumstellar gas. And you can see that the mass loss rate from gas and mass loss rate from dust, they are not aligning well with this 1:1 line, let's say. So this is because there is an uncertainty in the conversion factor, because this conversion factor, which we use to convert the mass loss rate in dust to the total mass loss rate, is mostly hand-woven. And so due to this conversion factor, which can be different based on which mass loss prescription we are using, it's very difficult to not to like have the agreement with all the observations that we have. So now that we have talked about the problem with the empirical and observationals, let's try to address this problem. So the first thing that we can do to address this problem is to understand the mass loss mechanisms in red supergiants. And these are all the mechanisms that are proposed until now for red supergiants. The bottom row here is basically all the mechanisms that can take the material from the star to the point until where the dust can form, or the material can go a bit above at certain distance from the star. And then after this, from this point onwards to the infinity, these major pressures mechanism can play a role to take this material from this particular point to the infinity in order to have this huge mass loss from red supergiants. I'm also very thankful to Von Loon to share with me this beautiful plot, which shows us that how different mechanisms are working at what distance from the star, how it depends on the effective temperature and also the spectral type. So based on the spectral type, which mechanism is more dominant than the other one. So this is a very nice visual representation of all the of all the mechanisms. But I'm going to talk about all of them one by one, so we know what we are talking about. So first, let's go to the radial pulsation. The idea of radial pulsation is that when a star expand, it throw the material outward, and when it contract, the material falls back. And so if the pulsation is high, what will happen is that it will drive the material out from the star to a greater distance. Now here the challenge is that for the red supergiant stars, the pulsations are very weak in comparison to AGB stars. And the temperature is high in the star, which means that to take the material to the point where it can form the dust, it has to go a bit far for the material to cool down and finally reach into the dust condensation zone to have the dust, and then other for example, radiation pressure on dust and these kind of mechanisms can take material from there. But because we have the weaker pulsation, already the material that is coming out of the star is very less in comparison to what we expect from the huge mass loss in RSGs. Then it takes us to the next theoretical model, which is convection-driven mass loss. What it suggests is that RSGs have, which is red supergiant star, sorry, I'm saying it in short, RSGs. So RSGs have large, fast-moving convective cells in their outer layer, and from this convection, it create the turbulent pressure, which lower the effective gravity, and then it helps the weak forces to eject the material. So basically, the whole point of convection is that it can create the turbulent pressure, it can lower down the effective gravity, but it definitely needs like a help from other mechanisms to help it to take the material really far from the star. So this is one of the challenge that first of all, it needs some other material as a help. And another thing is that the energy that is transported from convection can dissipate quickly. And so and we don't even have the strong observational support that supports to say that we have huge mass ejection due to convection in RSGs. Then coming to the third proposed theoretical model, it's supra-Eddington mass loss. So what we know is that the Eddington-limit is maximum luminosity before the radiation pressure can overcome gravity. And we know that it is that Eddington luminosity is inversely proportional to the opacity. So what happens in RSGs is that at the subsurfaces of the RSGs, due to the partial ionization of the hydrogen, the opacity can increase. And because the opacity is increasing, at that local point, the local Eddington luminosity can decrease. But now we still have the total luminosity of the star as same, and this creates the instability, which leads to the huge eruption of the mass loss, basically. Now, the challenge here is that basically in this phase, the the star is not in the hydrostatic equilibrium, and so it is very hard to model. And it depends on this instabilities that I just talked about, and these are not properly understood, let's say, and we don't have a direct observation evidence as well for this. Now let's talk about the fourth theoretical model. It's L1 waves. So what it proposed is that the magnetic field perturbation, when it propagates as L1 waves, these waves can transfer energy and momentum to the outer gas layer, which can be accelerated, especially if the gas is ionized. Now, the challenge here is that because most of the that RSGs have mostly neutral atmosphere, we don't have ionized gas as such. And also the observed magnetic field is too weak to have like a huge mass loss due to Kelvin waves. So this is like the limitation for Kelvin wave mechanism for RSGs. So once we have the material a bit far from the star by any of the mechanism that we just discussed, now what will happen after that? After that, radiation pressure on dust, which is most widely accepted mechanism, comes into play. So what happens here is that photons from the star push the dust grains in the outer atmosphere, and these dust grains can accelerate and drag the gas molecules, and we can have the mass loss. But as I said, the condition is that there should be a dust formation which should be close to the star. And it should be opaque at IR wavelength, because this is the wavelength where RSGs emit most of their light. But the challenge here is that not all RSGs form enough dust. And as I said, that in comparison to AGB stars, which are asymptotic giant branch stars, the effective temperature of RSGs are much higher, which means that the dust needs to, or the material needs to really go a bit more further than the star. And so it may be too far to be effective and can have the huge mass loss that we predict, that we observe basically for RSGs. Another thing is, of course, that we need some other mechanism to lift the material to the point where the dust can reach, the dust can form. Another proposed mechanism, if not radiation pressure on dust, is radiation pressure on molecular lines, which is basically the same concept, but here the radiation pressure is on molecular lines. So this radiation pressure Doppler shifted the molecular lines, and these molecules can absorb the stellar photons and can get accelerated and derive the mass loss, basically. So this is the whole concept. Now here, you can say the positive thing is that we do observe the extended carbon monoxide and H2O layers. For example, this picture that you can see here we do have some carbon monoxide. You can see in the magenta color that we do have these lines present. But there is this caveat, because here in these stars, the molecular lines are very closely spaced. So what happened is that when they are Doppler shifted, one line can come to the shadow of the other. And this means that the photons cannot access the opacity due to this Doppler shifting, because the lines are really close and kind of like blended. And so this can reduce the effectiveness of radiation pressure on molecular lines driven mass loss in RSGs. Then the third major theoretical model that was suggested is turbulent pressure driven mass loss, because this does not need radiation or dust. So this is kind of like similar to Parker's thermal wind model, if you know, because Parker's thermal wind model, it suggests that the corona of it suggests that the thermal pressure is the main driver of the mass loss, basically. And so what they did is they took the same concept and applied it to the red supergiant stars, and they say that in place of thermal pressure, we have the turbulent pressure. So the turbulent pressure and the ramp pressure, which is due to the convection here, can derive the mass loss without relying on the radiation or the dust. And this is something that is also shown by Key in one of his paper. So here the plus points here are the observed turbulent velocity, and the dots are the theoretical turbulent velocity. And you can see that the theoretical turbulent velocity is lower than mostly lower than what we have for the observation, which means that the turbulent pressure should be more than enough to drive the mass loss in RSGs. So after telling you all these mechanisms, I still want to say that it's still under the revision, that which is the dominant mechanism, or which mechanisms combined with which mechanism to drive the huge mass loss in RSGs. It's still all like an open field, and the work is still going on. So after this, I would like to talk about I would like to come back to the point where I said that the mass loss also influences the star's future evolution and even the final remnant. And this takes us to the famous supernova progenitor problem, basically. So what is this problem? You remember in the first slide when I was describing how the red supergiants can end their life. Type 2p supernovas can have are expected to have the red supergiant progenitors with initial mass of 8 to 25 solar masses. But pre-explosion images showed that there is a lack of high mass red supergiants. Now, this mass ranges depend on which stellar evolutionary track you are using, but so to say that high mass progenitors are missing. And this discrepancy is known as the famous red supergiant problem, or red supergiant progenitor luminosity problem. So this problem was approached by Smart in 2015. And what he did, he created a volume and time limited sample of 45 core collapse supernova, and he used the archival images, pre-explosion images, mostly from Hubble Space Telescopes. And this is this is the plot that he used to describe this problem. So what we see here is that we have the effective temperature, we have the luminosity. These data points here, the black ones, these are the detections. And the inverted red triangles are the upper limits. And these are the stellar tracks. These lines are the stellar tracks, which is from Eldridge and Tout. So what we see here is that there is no detection above the luminosity limit of 5.1, which if we translate into mass using this particular stellar track, it will come to 18 solar mass. So this implies that progenitors above 18 solar masses are missing. Now you can say, but this point we see here, this is exceeding the limit. Yes, but we don't know the nature of the supernova, basically. So we cannot conclude anything from this one point. Okay, so we have the problem. Again, what they did is they took the explosion models, basically supernova explosion models for different progenitor masses. So 12 solar mass, 15 solar mass, 19 solar mass, 25 solar mass. They took the data of the supernovas. Here, what we are plotting is the luminosity of oxygen, which is basically normalized here. And what you can see is that the observed supernovas are basically all around 12 to 15 solar masses. So it's for sure below the 19 solar mass limit. So which again says that we are missing the progenitors above mass 19 solar masses. So what could be the solution? One of the solution, and thanks to Key again for sharing this beautiful plot with me, One of the solution is change the mass loss rate, basically. So here what we have is the mass loss rate with Dieger, and here Key actually changed the mass loss rate, and you can see that the evolutionary track basically changed. For some of the stars, they will not even go to the red supergiant phase. So if we can change the mass loss rate, and we already know that I already said that there are discrepancies in calculating the mass loss rate and all these things. If we can change them, then maybe the problem will be solved. Another solution that Smart actually suggested in his paper is compactness factor. What is compactness factor? Basically, it measures how tightly your stellar core is at collapse. So if it's more, it means that the star will collapse and not explode. Here we are using different models again. And okay, based on which model you will look at, you will have different conclusion for sure. But just to say that if we look at these 4 points here in the red, we see that between 20 to 30 solar masses, the compactness factor is high, which means that one of the potential solution is that these stars do not explode, but they collapse in between these solar masses. They collapse directly into the black hole. So this could be one of the potential solution. Now this problem was revisited by Beezer in 2025. What she did is she took the sample of red supergiants in M31, and she took the one-band photometry data, like I-band photometry data. She estimated the luminosity, compared it with the full SED luminosity. So we know that the errors that we get on the luminosity, I can go back and show you, for example, this, because I forget to say sorry, but you see the error bars here. These error bars in the luminosity is basically because of the extinction, the uncertainty on the extinction, volumetric correction, distances estimation. So what she did is she said that, what if I change the volumetric correction? And you see that once she changed the volumetric correction, which depends definitely on the spectral type, you see the distribution got shifted. Obviously, we cannot take away the scatter, but it is now kind of like aligning, right? Then what she did is, this is the cumulative luminosity distribution she plotted for the supernovas. These are all observations. What she did is that this is the white one is 1 sigma distribution. This is a 2 sigma, 3 sigma distribution. And what she did is she took into account 0.2 dex of uncertainties more than the standard uncertainties. And now the plot got shifted a bit to the right, which means that now we have some data on the higher luminosity end as well. Similarly, like she took the same thing and she plotted it here. So she took the, so here we have the minimum luminosity, here we have the maximum luminosity distribution, and it is with the different uncertainty contours. So this is the standard photometry. This is the same as this thing. And then she updated the uncertainty, again taking into account additional 0.2 dex uncertainty, and the plot got a bit shifted to the higher luminosity. Now, by both of these plots, what she wanted to make the point is that basically maybe what we are doing is that we are underestimating the errors that we get on the observations, which means that there are supernovas that are present at the that have the high mass red supergiants, but because we are not taking all the uncertainties into account, we are missing them basically. So she called it like, maybe this is an artificially created problem. This is not a real problem. So Being said this problem is still under revision. We definitely need better mass loss models. We definitely need better evolutionary model. We need better observations for sure. And depending on that, maybe our uncertainties will not increase, but decrease. It all depends. As I said, that all these error bars, uncertainties depend on how we model the extinction, what volumetric correction that we are using, which also means that we need to take into account that the correct spectral type of each star. And then we definitely need multi-band pre-explosion coverage. Maybe we can rely on multivalent observations by, for example, JWST for high-resolution images to solve the problem. And with this, we come to the end. I want to say that this is a very open field. A lot of discussion is going on what is the actual mechanism of the mass loss rate, how to solve this famous supernova progenitor problem. We definitely need better, more observation and models to solve all these problems. So that's it. Thank you.
Thank you very much, Jahanvi, for your outlook about red supergiant winds. This was a lot of information. Do we have question in the audience? Yes, RMH, you can speak up.
Hi, this is Roberta Humphreys at the University of Minnesota. Thanks for mentioning the Humphreys-Davidson limit. Personally, I'm not convinced it's that directly relevant to the red supergiants, more relevant to the progenitors, the hotter massive stars. But I actually have a point I want to make, mainly for information for people. I'm currently the guest editor on a special issue on red supergiants being published by MDPI. So I wanted to draw that to your attention. We have 8 review papers that will be published in this special issue. 5 of them are already now posted on the website for the special issue. They include, naturally, a review on mass loss in red supergiants by Jaco van Loon, who I see is logged on here this morning, a special paper on Betelgeuse, a paper on RSGs as supernova progenitors, interesting paper on both the red and yellow hypergiants, which may be very relevant to the red supergiant problem. And I also just wanted to point that out, that this special issue will be coming out very shortly. We're going to be posting the papers on the archive and the Massive Stars newsletter. But just one comment on the science being presented here. I noticed that you didn't mention the possibility of what I might just say high mass loss episodes in the red supergiants. Specifically, remember what happened to Betelgeuse, high mass loss, ejection, etc. In a star in more extreme red supergiant like VY Canis Majoris, we see evidence there were about 6 of these deep dimmings or high mass loss episodes in a 30-year period in its light curve in the early 20th century. RWCVI, a very luminous K-type supergiant, has been observed to have an event similar to that of Betelgeuse. So there are other things happening. I think these mass loss episodes we're seeing, these dimming episodes, are obviously related to surface activity, which may be connected to convection. And with regard to the red supergiant problem, you didn't mention the possibility that those missing red supergiants may be evolving to warmer temperatures through a yellow hypergiant stage before they go supernova. So that's another possibility. And also that possibility is driven by mass loss. So thanks, very good, excellent review.
Thank you. Actually, you are right. I did not mention it, but I mentioned it in the slide. I forgot to say it verbally because if you look at my slide, I did say that one of the thing is, okay, it's somewhere. I have to find it. Anyways, thank you.
Okay, thank you, Roberta, for this very long comment. Do we have other questions? Yes, we have Yes, Sutira, maybe you can speak up. No, he has disappeared. Okay.
Hello, am I audible?
Yes, please go ahead.
Yeah. Oh, sorry. Sorry, I was on mute. Uh, I was mentioning that you mentioned a bit about radial pulsations and that driving mass loss. But in red supergiants, the pulsations are not strong enough to drive the material to large enough distances for dust-driven mass loss, right? But there have been some ideas in the past, like a work by Jung and and others thereafter, where pulsations could induce shocks, so supersonic speeds in the RSG envelopes, and that could lead to dynamical timescale mass loss, like ejections and eruptions. So there has been very little work on it, but there has been some indications that that could drive, without dust formation, that could itself directly lead to enhanced mass loss. So I just wanted to mention.
Thank you so much. I must have missed this paper. It's very interesting to know that something like this also have been discussed. I'm not really in the field. But yes, if you would like to share this
Yeah,
this
sure.
paper
We are
with
also working on
everyone,
a
yeah.
paper. Yeah, we are also working on that idea to explain supernova dense environments around supernova. So maybe you look out for our paper sometime.
Thank you. I will definitely. It's very interesting. Thank you.
Okay, thank you very much. Do we have really questions or other comments? I don't see any. This is your...
Sorry, can we ask a question from the Leuven room here?
Yes, sure. Please go ahead.
So you outlined quite a bit of various possibilities in the physics that drive the main mass loss here for the red supergiants. But at the end, you also showed this, and of course, I know this since it's from Dylan Key and myself, right? That the observed turbulent velocities are actually enough that you don't need anything else to explain them. So I guess my question is then, isn't it just a matter of identifying where this turbulent pressure originates from?
Hi, Jan. Yes, you know I agree. So yes.
But I was in view of what you have learned about the difference. I was asking the speaker now. In view of what you have learned about the different mechanisms that are proposed, right?
Yes.
Have you formed an opinion? What do you think is most reasonable? Like I said, it's pretty clear what Dylan and I think, but I'm also interested in hearing what other people think. Because I would say we know a lot about the physics of these stars now. So I wouldn't say we don't, but I don't know what you, after having studied now the topic, I don't know if you.
Yeah, I mean, I kind of agree, and I think because that's the reason that why I showed a result here from this paper, and in every other I did not show anything, because I think that I agree with with this, but also I feel that this depends on how you are modeling, which parameters you are using, which mass loss prescription you are using. So if you are asking my opinion, that what I think is the is the winner in the mechanism, I don't have any, to be honest. because I really think that it depends on how you are modeling, which parameters you are taking into account. But I agree with the fact that you mentioned that it also depends on where the turbulent pressure is created. Yes.
Yeah, I would say that's the real challenge. Now look, identifying where this, well, these observed values then come from. Because if they're there, mass will spill out. That's what I would say. Yeah. Okay, thanks.
Okay, thank you.
Thank you. Do we have other comments, questions for the speaker? This is your very last chance now. No, then I suggest we thank the speaker again.
Thank you.
Oh, maybe I can say something, since
Sure.
this is a